We're moving on to Chapter 7. Chapter 7 deals with, and this is my favorite stuff of the whole semester, chemical reactions. Not that it's all downhill afterwards, but this is the stuff that when I was in school, I was actually a math and music double major, and it got me to change to chemistry. So the first thing we're going to do is we're going to look at, I have some balloons here, and you'll notice that during the semester I like to revisit certain things because they're A, fun, but B, when we bring them up, of course we try to learn something new every time we bring them up. And of course, what might we find in these balloons? Helium. Sure, what else could we find in them? Hydrogen. And by the way, if you inhale this stuff, now I gave it to a student to inhale earlier today.
But they kind of blew it. They didn't know how to inhale. If you haven't done this before, you gotta know how to inhale, right? So,
if you don't know how to inhale, then just don't do it.
And the other thing you gotta be careful of is if you inhale. Sometimes if you inhale too much and you don't have enough oxygen to go to your head, your lips start turning blue, like mine are probably turning blue right now, right? No?
Okay, so sometimes you're a little weak in the head, and you know you get a little lightheaded, and so you got to be careful so you don't cut off the supply of oxygen to your head too much.
Isn't there a gas that you can inhale that has the opposite effect of helium?
There is. Yeah, there is. Have any of you ever Googled your chemistry professor? All right, you might do it sometime. Okay. So, anyhow, we'll look at it later this semester. But we're going to go ahead, and we just have to go ahead and ignite this stuff.
It's under your pen.
Where is it? Right here? All right. So, if you get startled easily, you might want to cover your ears. We'll go with this one here. And then we'll go with this one here. Wow, that was good. Okay, so first one over here would have been?
Helium.
Helium. Second one over here would have been? Hydrogen. Which can only mean that I saved the best for last. And this one here contains a mixture of?
Both.
Well, not both. Hydrogen and oxygen. In fact, when I put it in here, I put in 2 parts of hydrogen for every 1 part of oxygen. And there's a reason why I want to put in 2 parts to 1 part, because we make water. And so what we're going to do here is we're going to make some water. But I need some ear protection for this one. And you're going to have to cover your ears for this one as well. And so I'll keep an eye on it here for you. So cover your ears. Now it used to be like auto dial to 911 or something like that. And so they had to change that because I knocked the phone off the hook too much. It wasn't 911, it was to the info desk. You know, and then they would be going, hey, you know, you hang it up and they'd be calling you back wondering what's wrong. You know, because there's this boom on the other side. But now, what we like to do here is we'd like to write out a description of what we just saw. So, to write out a description, let's first of all talk about the gases that were in the balloon. And those gases again were?
Hydrogen, helium.
Okay, the very last one. Hydrogen, right. So we'd say the hydrogen gas reacts with, what else was in there? Oxygen gas. To produce, and what did we make? Water. In which phase?
Gaseous.
Gaseous phase, exactly. Because we did not get splashed with water in the front. We produce the water in the gaseous phase. So now, we'd like to write out a chemical equation that shows this reaction. So the formula for hydrogen gas is almost. What is the formula for hydrogen gas? H2, right. And why is it H2? Always partnered up. It's one of those diatomic elements. In case you've forgotten your diatomic elements, you need to remember them. They are hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. And our mnemonic was Honkelbrief. In case you've forgotten that, Honkelbrief. And so when we find these elements by themselves, we find them always paired up with another atom of themselves. And these are the 7 diatomic elements that you need to know. So then we go back to putting in parentheses, because it's a gas, it would be G, right. And then we react it with oxygen, which has a formula of O2. And in parentheses, G. And then we are making H2O with the label of G. Now these things that we're putting afterwards are what we call phase labels. And we've seen one of those phase labels already. The one we saw here last week was aqueous. And G then would be gas. The other two would be solid and liquid. And they would be L, well, S and L based on how we stated them. But these are the different phase labels that we would use. And so when we want to show what the phases are in the reactions, we include these phase labels. Now some other terminology that we need to be familiar with are these, and they are the terms reactants and products. Yes, sir?
Where's the extra oxygen go?
Where did that? Very good. I'm glad you brought that up. We're going to look at that next. Okay. So what the question was, where did the extra oxygen go? So we're going to deal with that here in just a moment. All right. So if you're running a business and you want to make something, the stuff you make is called a product. So the products are what we have at the end, and the reactants are what we start with. Okay, so there should never be any confusion, because if you're making something, you are making a product. And so the reactants are what we start with. These are your raw materials. Now chemical equations can have one or more reactants. In this case, how many reactants are we showing? 2. And they may also have one or more products. In this case, we're showing how many products? 1. Okay? And so reactants and products are separated with an arrow, and the reactants on the same side are separated with a plus sign. Products on the same side would also be separated by a plus sign as well. So now, the question here was, what happens to that oxygen? So I'm glad you brought that up. If we look at a chemical reaction, what takes place here is this. What I've done here is I've made some models of hydrogen and oxygen. And so the hydrogen is represented by the white, and the oxygen is represented by the red. And what happens in chemical reactions is that molecules will collide with each other, and what will happen if the conditions are right is that some bonds will break and other bonds will reform. In this case, when they reform, we form that molecule of water, but as you asked, then what happens to that oxygen? And this is clearly showing that there is some oxygen left over. And we can't have that, because if we take this away, we have basically defied the law of conservation of matter, or mass, which says we can neither create matter nor destroy matter as a result of a chemical reaction. So what I'm going to do here is I'm going to put these back together. And once I put them back together, what I'm going to do next then is I'm going to put a second molecule of water up here. And when I have 2 molecules of water, what I'm going to do then is I have to come back to the chemical equation and show that I have 2 molecules of water by writing a 2 in front of the H2. Just like this here. So now I'm going to start with 2 molecules of hydrogen, and I don't write the number in front of the oxygen here, but what number is here if I were to write it? Right, and 1s are implied. They're not zeros, it's a 1, but the 1s are always implied, just like they are in the chemical formulas. So now, if I come back here, once again we have a chemical reaction. What's going to happen is that they're going to collide with each other. Some bonds are going to break, and other bonds are going to reform. And so we put these together here. We make a molecule of water. We put these together here. And in the end, we have how many molecules of water?
2.
Right. And what do we have left over? Nothing. Okay? So there's nothing left over from here. So if we want to show then that we made 2 water molecules, what would we do in our equation? Put a 2 in front of the water, exactly. And so when we put a 2 in front of the water, what this gives us is what we call a balanced chemical equation. Before we put the 2's in there, this was an unbalanced chemical equation. But a balanced chemical equation is one that conforms to the law of conservation of matter. The numbers that we have out in front here are called coefficients. And where else have you heard of coefficients before? Math, right? And what do they stand for in math? If we saw something like 2y, what does 2y mean? It means 2 times y. It means 2 times y. The operation there is multiplication. And if we saw something like 2xy, this means 2 times x times y. Okay? Now, when we write out coefficients, where are coefficients always written in algebra? At the front, right? We never write it x2y. Okay, we always write it with the coefficient in the front. And so the same is true with coefficients in chemical equations. The way that they are always written is out at the front of the formula, never tucked into the middle. So we then look at another reaction that we did earlier this semester. And this one now is going to involve some magnesium. So we're going to turn the lights down for this one once again. I always think it's important to test by fire. So we're going to test by fire. And, oh yeah, you need to see this. So we're going to put it up on the dot cam and bring the light back so you can see the metal. Come on. Sometimes it takes a while for that focus to kick in. That's probably that reflection that's on there. Okay, well then we can't see it. Here's the metal. Alright. So we're going to go ahead and react this. And this once again is one that you should not look at directly. So when you observe this one, either look at the screen or look up here just off to the side. Not directly at this. Burns out. And now if we wind up looking at the product of this reaction, we should see that we produced a white powder at the end. Okay, now this actually used to be a very common reaction, but again this is one that starts to show my age, because there used to be a thing called flash bulbs. Anybody know what flash bulbs are?
On camera?
On the cameras, yeah. But there used to be one-time use, those flash bulbs, and what it was
is you put it in the camera, and you didn't take selfies in because then you wasted film. Okay, you have to put it in the film. And then you'd have to develop it, you know, and take like a week to get your pictures back. But the old flash bulbs had some very thin filaments of magnesium in there. When you snapped on it, what happened is that that magnesium would get ignited with the oxygen and produce a big flash, and then it was over. And you know then how you could tell that they were used? Okay, the bulbs were coated with plastic. And so then you would check to see if the plastic had melted, and if the plastic melted, that means you had already used it. So that's what we used to do. God, I feel so old when I say that. But anyhow, yes, no selfies, take a week. You wouldn't know what would happen. You wouldn't waste in a selfie, that's for sure. But if we want to write out a reaction then, here's what we do. Let's first of all write out a description for the reaction. And that description would look like this. We would say that magnesium metal reacts with, and what do you suppose it reacts with? It's got to be a chemical. It doesn't react with the flame. What do you think causes us to burn? Oxygen, sure. So it reacts with oxygen gas to produce. There's not a whole lot you can make with magnesium and oxygen. It's going to have to be magnesium oxide. Can't be anything else. There's nothing else there. So it's going to have to be magnesium oxide. And that magnesium oxide is in which phase? Right, we see here that it's a solid. So now, let's write out a chemical equation that shows this reaction. Magnesium has a formula of Mg. Should we put Mg2? No, because it is not diatomic. Which phase did it come in?
Solid.
Right. So then we're reacting with oxygen, which has the formula of O2. Phase label is G. And then we make magnesium oxide, which is going to be Mg,
O2.
not O2. And it's not O2 because, and this is where we can't forget what we learned in chapter 5. What is the charge on the magnesium? 2 plus. What is the charge on the oxygen? 2 minus. Alright, so if we have a 2 plus and a 2 minus, what happens to those charges? They cancel out. And the formula becomes MgO. And so then the phase label here winds up being S. Now, then the question is, again, what happens to the oxygen? Okay? Well, in order to make them the same, we have to balance the chemical equation. So to balance it then, what we do is we look at the magnesiums, and how many magnesiums do we see on each side? 1 here and 1 here. How many oxygens on the left?
2.
How many on the right? 1. Now when we balance, we can't change subscripts down here because that changes the formula. So the only way we can balance is to use a coefficient, and that coefficient goes in the front of the formula. But of course, now once we put this up here, that also screws up the magnesium because now we have 2 magnesiums over here. So in order to balance this, we need 2 in front of the Mg to make this a balanced chemical equation. And now we haven't lost anything. All right, next up. If you have any questions, just stop at any point. Raise your hand. Nitrogen gas reacts with oxygen gas. No, not oxygen, I wanted hydrogen. There we go. Reacts with hydrogen gas.
to produce gaseous ammonia. Let's write out a balanced chemical equation for this reaction. Let's write out a balanced chemical equation. We start with the nitrogen, which has a formula of N2. Phase label is G. React it with hydrogen gas, which has a formula of H2. G. And ammonia, now we learned today, is NH3. And this is a gas as well. Now here's where we need to start learning some strategies in order to balance our chemical equations. And one of those strategies is to use what's called the least common multiple. So if we look at hydrogen, we see how many hydrogens on the left
2,
and how many on the right.
3,
And so once we find the least common multiple between 3 and 2 and come up with
6.
6. So if we wanted to make 6 hydrogens, what number do we need right here? And what number do we need right here? Right, and we do that, we wind up with 6 hydrogens on the right, 6 hydrogens on the left, and that then is balanced. How many nitrogens here? And how many nitrogens here? 2. And that's balanced as well. Now some of you are going to have an easier time if you make a table and try to track them. Now, if you know how to balance just the way we did, you don't need to do this. But again, for some of you, if you have trouble with it, might be to make a table looking something like this, where you make your elements, N and H. And you kind of go back to where we started with then, before we balanced it, and you ask yourselves, how many nitrogens are on the left? Well, you see that there are 2 here, and you look on this side and we see that there's how many nitrogens here? 1. If you look at hydrogens, how many are here? 2. And over here we have 3. So you can start by making some sort of table where you then wind up trying to account for each one of them. And maybe instead of starting with the hydrogen, you'd start with the nitrogen. If you see 2 here and you see 1 here, the most logical number to put in front of this would be a 2. And of course, if you put a 2 in front of the NH3, you're now going to have 2 nitrogens on the right, and you're going to have a total of 6 hydrogens on the right as well. Well, now we can see that the nitrogens are balanced. To balance the hydrogens, we then put in a 3 in front of the H2. It winds up giving us a total of 6 hydrogens on the left-hand side, and they're now balanced. So for some of you, you may find it useful to do this at least once you get started, and once you've done this a few times, you'll probably have a little more success. Okay, any questions on these examples? Okay, let's try these. And these are going to come up now in the Socrative app. Let's balance these 3 equations. We have V, and now I'm going to leave out the phase labels on this one. V plus O2 yields V2O5. Next one is going to be Al plus O2 yields Al2O3. And the last one is going to be KClO3 yields KCl plus O2. So take a few minutes here, help each other out. If you have some questions, ask on the balance. 5, 4, 3, 2, 1. Correct answer is 5. Very good. 5. And if I had to come back here and to balance it, let's go through all the coefficients on this first one. What goes in front of the V? I hear 2 and I hear 4. What is it? 4. And in front of the O2 there would be a 5. And in front of the V2O5 there would be 2. So it'd be 4, 5, and 2. So get the next one balanced. This one we're going to give you less time on. This one is asking for the sum. In other words, sum together the coefficients. When balanced with the smallest whole number coefficients. Remember, if you don't write a coefficient in front of it, the coefficient is equal to 1. It's not 0. It's 1. So we'll take about 15 more seconds. Get your answers locked in. Let's count down. 5, 4, 3, 2, 1. Correct answer here is 9. It's 9 for the sum. Now to arrive at that, let's talk about the coefficients. In front of the aluminum there would be 4. Where are those numbers going? That's one thing I don't like here, Windows 7. Alright, 4. And what goes in front of the O2? 3. In front of the Al2O3 it would be a 2. And so if we sum together 4 plus 3 plus 2, we get 9. Okay, let's do the last one. When balanced with the smallest whole number coefficients, the coefficient on KCl is give me about 30 seconds here. Let's get your answers locked in. We'll count down. 5, 4, 3, 2, 1. And it is a 2. And this one here, if we balance it, what are the coefficients from left to right? They are 2, 2, and 3. And probably the key to this one is the least common multiple between the 3 and 2. Least common multiple of 3 and 2 is 6. So to get 6 oxygens, we have to put a 2 in front of here. To make 6 oxygens over here, we need a 3 in front of here. Because we then put the 2 in front of the KClO3, we then need to put a 2 in front of the KCl.